all of you to the HIF seminar. This is probably the largest seminar we've had in our program. It is normally about research in set theory. Who advertised this to all of the CMS so that this crowd showed up? Thomas, is that you?
It's on the TV screens.
Yes. Well, Monday's talk was on the TV screens. Anyway, so
it also goes out on email from talks.camp.
okay. Well, so
Some of us still are students.
it's very nice to have all of you here, and I'm not going to waste any more time introducing our speaker because you all know John Conway, who will first give a talk on the Surreal numbers, and then there will be a short break, and then there will be a special talk that we hear after that.
The other talk is, I'm rather hoping that just a few people will come and that it will be a sort of rather less formal talk. Well, actually, this talk isn't going to be formal either, but what I really mean, more sort of conversational and, people questioning and so on. However, the Surreal numbers, let me talk about the Surreal numbers. The Surreal numbers were really the greatest mathematical surprise of my life. It was very strange. They happened as a consequence of the fact that at the time the British Go champion was in the Cambridge math department. And he used to bring his Go playing friends in occasionally, and while a game was going on, other people, perhaps not quite so good at Go, would try to sort of talk about why this move was better than that one and so on. And I sort of tried to understand the game of Go, and I didn't ever succeed in understanding the game of Go, let me say that straight away. But I did notice that near the end of the game, it divided into what I call a sum of games. You had a number of empty regions, and the rules of the game forced you to choose which region you were going to move in, and then make a move that would be legal if that region were the whole of the game, legal for you. And okay, so now there's a rather trivial mathematical theory of Nim-like games, which are really about sums of games in which the games have this rather unusual property. I mean, unusual in the sense that most games don't have the property, that the legal moves are exactly the same for each player. Standard example is actually the game of Nim, where the move is to remove some counters from one of the heaps of counters on the table in front of you, and then your opponent makes a similar choice, and you're just alternating. And in these alternating moves, there's no compulsion to move in the same component as your opponent just moved in, or in a different one. You're totally free each time. And the theory is that every such game is essentially equivalent to the game of Nim. There's a dictionary of positions in your game, your favorite game, whatever it is, to positions in one heap Nim game. The thing is the sum of Nim games of one heap. A Nim game of one heap is not very interesting. You've got a collection of counters or beans or something. When it's your turn to move, you reduce the size of that collection, and the person who wins is usually the last player to move. Well, it's very easy to play that game. You just take the whole heap and remove it, and then call on your opponent to move, and he can't, so he's lost, or she can't, perhaps, let's say. But that's not enough. To know who wins the one heap game. Oh, by the way, it's not always the first player to move who wins the one heap game. Here's a little test for you. When is it the second player to move? You failed the test! And it's perfectly obvious. When you start with the empty heap, the simplest position of all, then the second player wins because you can't move. Okay, it's really important to get things right at zero. Not only in this kind of game theory, but in all of mathematics. You've got to get things right at zero, and you should really start at zero, not at anything larger. Anyway, never mind. So I'll forgive you. Gave me the opportunity to shout, which is always rather nice. Anyway, so okay, but it shows that knowing who wins the one heap game isn't much use in knowing who wins the n heap game. You need to know rather more about the heaps than whether they're zero or not. The theory is well known, and I won't bother to redevelop it. The answer is there's a function called the Nim sum by game players, and exclusive or by computer people, and it's got various other names. You add the sizes of the heaps in binary without carry, and if the sum is zero, then but that controls who wins. And in fact, so let me give an example. So if you have a heap of size 5 and a heap of size 6 and a heap of size n, which I'm not going to tell you for the moment, I'm wondering for what value of n, well, for what values of n does the first player win, and for what values of n does the second player win? And well, this rule that I said about adding in binary without carry is actually, it says what Nim heap your given game is equivalent to. Every game is equivalent to a single Nim heap. And so, for instance, a Nim heap of size 5 and a Nim heap of size 6, well, 5 is 4 and 1, 6 is 4 and 2, so we cancel the two 4s, and then we get the answer is 1 and 2, which makes 3. So the answer is a Nim heap of size 5 and a Nim heap of size 6 is precisely equivalent. I don't know what that means. I'll tell you later, though. I expect to learn. A Nim heap of size 5 and a Nim heap of size 6 is precisely equivalent to a Nim heap of size 3. Now I'll tell you what it means to this notion of equivalence. It means that whatever game you add them to has the same outcome as if you just added 3 to that other game. The other game is conventionally called a test game. Okay, so that's that. So a Nim heap of size 5 and a Nim heap of size 6 is equivalent to a Nim heap of size 3. Now 5, a 6 and an n was the problem I started off giving you. Who wins that? Well, it's a 3 and an n. Now when is a 3 and an n equivalent to a 0? Well, certainly if n is equal to 3, because 3 plus 3 is 0. Plus will mean Nim addition, at the moment anyway. And 3 plus anything else is obviously not 0. So the answer is 5 and 6 and n is won by the first player unless n is equal to 3 when it's won by the second player. Okay, so well that's all nonsense. It's about Nim and so on. But I had decided, I decided a long time before this wonderful Go player turned up in the math department to try and study sums of games in which it wasn't true that the games had the same legal moves for each player. And somehow I'd never got round to it. I was just lazy and so on. And watching these Go games going on and realizing the importance for Go, very difficult game to understand, of the notion of sum of games, was the spur that sort of pushed me to actually do some work for a change. Okay, that's that. Now, let me discuss the concept of a game I'm going to consider. There are all sorts of games, but I'm going to use them for games in which there are two players and the turn alternates. The player, one player makes just one move and another player, his opponent, then makes a reply to that and so on. I usually think of, I certainly call the two players left and right. Let me sort of draw what has sort of happened here. Here, I'm no good at drawing figures. In fact, I'm not much good at drawing anything. So I'm going to suppose that left and right have just left the room for a moment. And, whoops. And here's right's chair, and they've got these letters L and R drawn on each side. Even if you were on the other side, you'd see the same letters. And they've got they're playing the sum of chess and drafts. I'm only vaguely suggesting these things. In fact, I'm not really considering the sum of chess and drafts because those are much too complicated games for me to think about. Okay, oh sorry, I can't see the feet of legs of right's chair, and I think I should be able to. Okay, well, that'll be good enough. Okay, and that's the situation. When they come back, they'll seat themselves on the chair, and whoever's turn it is will make the next move, and so on. Okay, so there's what I want you to see. Now, when you consider playing that sort of game, even if the games you're considering have the property that legal moves alternate in them, that's not necessarily so. For instance, if we have a TV camera focused on the chess game, that TV camera will see perhaps several consecutive moves by the player called white, which actually that rhymes with right, but never mind. So yes, you should understand that the sort of structure of a game in the structure of a game, you must allow several consecutive moves by the same player. In fact, an arbitrary number of consecutive moves by the same player. Even although, when discussing who wins and everything, we only have to consider alternating moves by the players. It's a little bit paradoxical. Okay, so there's the notion of a sum of games set up. Now, so what's the structure of a game? Well, the structure of a game is indicated by, whoops, oh, I see, by drawing its tree. And, okay, so the tree must have names along, the tree has the starting position as a node at the bottom of the tree, and other positions are nodes rather higher up the tree, and the moves are indicated by lines, arrowed lines joining one position to another, and those lines are marked with L and R, or else they're slanting to the left for L and slanting to the right for R, and then you don't have to mark them terribly much. And now, okay, so here is a very interesting example of a game. There is the tree. It's got just one position, which is called the initial position. It's illegal to make a move at any time for either player, and if, when it's your turn to move, you don't move, you lose. Okay? That's the game called Zero. It's not perhaps for many people a very interesting game to play, but in the mathematical analysis you've got to consider it first. Start at 0. Make sure your definitions work at 0, and then they're more likely to work later on. Okay, now let's consider 0 and another game that I'll call T. I'll tell you why I use that letter later. And the game T is played with a sort of packet of these coloured pens here. And I won't bother to say exactly what the rules are. You can just trust me. When I make a move in T, or talk about a move in T, that's the definition of legality, is when I make it, it's legal. Okay. But now I want to consider a slightly more complicated game, namely 0 plus T. Okay, and I shall suppose that it's my move at the beginning of 0 plus T. Well, I'm studying the situation. Look at 0, and I look at T. Ah, good. I don't think I'll move in 0. I'll move in T. And my move is going to be to take this orange pen of T. And then you've got to respond. I suspect you're not going to move in 0 either. So your move is that fortunately is legal. And so we carry on like that. Oh, by the way, any game when played alternately must come to an end, where that's part of the, let's call that part of the definition of a game. I was going to justify it in some way. Okay. Well, I don't know whether any of you have noticed a theorem. The theorem is that 0 plus T is isomorphic to T for all T. It's not actually the same. A position in 0 plus T has a piece of paper with a black spot to the left of T, and otherwise, just T. Not actually the same, but it's isomorphic. That's a complicated word, but I imagine you've heard words like that before. And the definition, the symbol we use for isomorphism is some kind of equality sign. This is a theorem, and it is that 0 plus T is isomorphic to T for all T. And it's actually got a for all T in here as a quantifier and so on. Now, that's a pretty good theorem. It's beginning to sound like mathematics, you must agree. And it deserves a number, so I shall call it theorem 0. Okay. Who wins 0? Come on, children. Who wins 0? Nobody listening. Player number 2, yes, that's right. Player number 2 wins 0. So let me just make a few more theorems. I won't bother to call them all by numbers, although I often do. Theorems. The outcome of 0 is player number 2. They're also definitions, the way I'm writing them down. Let's define another game. Oh, there are going to be some definitions as well. I'm going to define 1 to be this game. So this means that this is a game in which there are 2 positions. The initial position, which is represented by the node at the bottom, and the final position represented by a node at the top. And the only legal move is for left, and it's to move from the initial to the final position. I'm also going to introduce a new notation, so to speak, which is that is 0 / blank. In general, in this notation, you put left's options, which means the places you can get to from G in one move, if you're player left options to the left, see, it's handy mnemonic notation of this vertical line, and right options to the right. And you'll see that there needn't be a right option. There isn't in this game. In fact, there isn't, I should have put these in the wrong order. 0, let me pop it up here, is blank slash blank. Blank isn't the name of a position. I've just listed all the positions that left can move to from 0 to the left of this line, and all the positions that right can move to the right, and there aren't any of them. No legal move at all is available in 0. I hope you see that it is a good idea to start with these very simple games. Indeed, roughly speaking, we're only going to talk about games at this sort of level for the whole thing. I hope you don't talk about them too much, because I want to get it all said, and I haven't got all that much time. Oh my God. Okay, so, okay. Now, 0 is not equivalent to 1, because if left starts in 1, he makes a move to 0 and calls upon right to move, and she can't do so, and so left will win, but left doesn't win in the game 0 if he starts. He wins if the other person starts. Okay, so we've got 0 is not equivalent to 1. So the theory is obviously non-trivial. There are two distinct games in here. Okay, 1 is in fact greater than 0. It turns out, I'll tell you what greater than means. G is, this is a definition, G is greater than H means, let me define greater than or equal to, because it's a more fundamental relationship. That's if and only if left wins H plus T. T is the typical name for a test game, implies left wins G plus T. I've got to put parentheses around that so that you can sort of parse it properly. I've missed a bit of it out though. In the same circumstances, what that means is if left wins H plus T starting first, then left will win G plus T starting first. And if left wins H plus T starting second, then he will win G plus T starting second. I'm just leaving that, I'll just call that in the same circumstances. You know, whoever starts, or something. Perhaps whoever starts is a shorter thing to say than in the same circumstances. And then I'm going to define G less than or equal to H. Sorry? Yeah. To mean that H is greater than or equal to G. G is equal to H, but I'm sorry, it's really, I've already defined that, if and only if G, well, let's say H is greater than or equal to G, greater than or equal to H. The inequalities happen both ways around. G greater than H if and only if G is greater than or equal to H, and H is not greater than or equal to G, and a few other things like that. I'll just understand that you know what sort of things are going on. Okay. I haven't told you about numbers yet. All right. I'm now going to tell you a bit about numbers. I feel I've got to do it in a rush. Yes, I was just wondering whether I should give you some other examples first. Anyway, I call a game a number if all its options are numbers and every left option is less than every right option. And okay, so you notice that in the we've sort of not worried what games are really, in a sense. It was just explained by sort of trees of moves and so on. A game is a collection. A game, if you have two, oh yes, there's going to be a convention as well as definitions and theorems. There are quite a few conventions. Okay, and the best one is that G is equal to G left slash G right. That's actually a notational convention, and I'm not writing very much about what it means, but I'll say it now. What that means is that I'm going to use, that I intend to use G super L to indicate the typical thing I'm going to write to the left of in the definition of G, of the vertical slash, and G super R to be the other thing round, and those are called the options of G. The GLs, oops, the GLs are the left options and the GRs are the right options. Thank you very much. Oh, it fell out of my pocket. You can still hear it, can't you? I hope you can. Okay, you should hear me actually. Okay, so in order to make a game, you take any collection of games that you like and put them on the left of a slash, and then any other collection of games that you like, well, you don't have to like them actually, but never mind, and put them on the right hand side of the slash, and that's all games are made that way. It's interesting because you know, how does that procedure get started? Well, you already know. It appears at first sight as though you need some earlier games, but you don't. You can always have the empty set of earlier games and stick that both on the left and on the right and so on. We prove theorems by induction. If a theorem is true for all the options of G, say, if a theorem in which G is being proved, then if that implies that it's true for G, that's the way you prove theorems. That's really a transfinite induction. It doesn't look as though our games are going to get transfinite very soon, but they do. I'm going to sort of define 2. I'm going to say 2 is defined to equal, the colon on one side of the equality sign means that the thing on that side is being defined, 1 plus 1. Oh, but what is 1 plus 1? Well, aha. Oh yes, I've never defined addition. X plus y is xl plus y and x plus yl on the left. That's because if we're moving in x plus y, and we're the player left, we move in either x and leave y alone, in which case we've moved to xl plus y, etc. Well, I needn't continue that. And on the right hand side, the options are xr plus y, x plus yr. I'm sorry, I accidentally wrote an equality sign there instead of a plus sign. So there's the definition of addition. The definition of order is quite interesting. You already know it if you're thinking about games. It's that x is greater than or equal to y unless, and only unless, which is indicated by writing an extra letter at the end, unless some xr is less than or equal to y, or x is less than or equal to some yl. just about, yeah, okay, it's still in here. And that corresponds to the fact that when you're playing I haven't told you the difference. Oh my, well, I got that out of order. Minus x, the left options of minus x are the negatives of the right options of x. And there's a similar thing on the other side. So there's minus x. So what that means is minus x is the game got by reversing the legality of moves. Anything that was legal for left in x becomes legal for y. Sorry, legal for r, right, in minus x, and so on. Okay, so there's minus x. And now we can prove a number of theorems. What do I want to prove here? I tell you what, I'll prove that the associative law of addition. X plus y plus z, or z, I'm sorry, I've been in another country for too long. I'm going to prove that that is equal to x plus y plus z, you know, with the brackets arranged differently. And so that's a theorem. And the proof is, oh my. Well, wait, I think I'll prove an easier theorem first. Theorem. X plus y is equal to y plus x. Oh dearie me. It's not actually. It's isomorphic to. But after a time we just work modulo isomorphism. And it turns out that that's okay. It turns out, for instance, that if x is equal to x prime, is isomorphic to x prime, and y is isomorphic to y prime, then x plus y, believe it or not, is isomorphic to the other thing. So I'm going to prove that, and it goes that x plus y is equal, by definition, to x left plus y, x plus y left. I'm sorry, I'm going to have to squeeze it vertically. X plus y, x right plus y, x plus y right. And now in this thing, by induction, though this is induction here, we've already established this theorem about the sum of two games being the same if they're put in the order for xl and y, because that's an easier case of the theorem. And so xl plus y is actually equal to x plus yl. No, it's not. It's equal to y plus xl. And xr plus, no, x plus yl is equal to yl plus x. And then these things are equal to corresponding things as well. And this, by definition, is equal to y plus x. Oh, sorry, there's no parenthesis around there. Because y plus x has these options on the left and those options which you can't see on the right. Okay, that's called a one-line proof. Now, the one-line proof of this theorem is very similar. It goes x plus y plus z is equal to, and this is by definition, x plus y plus z left, and x left plus y plus z, and a bunch of other stuff. And then this is, this one, the second one there, is equal, the first one, by, curses, that's a definition, is x plus y left plus z, x plus, let me solve this problem. I define z to be z. X plus y left plus z. Oh, over here though, y plus z left is equal to either y left plus z or y plus z left. Oh my, it's going to take a long time before this line finishes. Now, I define in my book on this subject the concept of a one-line proof. A one-line proof is something where you just are proving some identity like this, and you work out what the left-hand side was defined to be, and then you use induction to say that the things in there are equal to the things that they are, and then you come out, you define it by induction the other way, and then by definition again, and my God, you get to the thing at the other end of the line, and that's a one-line proof. One-line proofs quite often take the whole length of the blackboard to do it. But they're still one-line proofs, even if they take several lines to write out. Okay, we've had enough of this, I'm sure. Okay, so now let me talk about numbers. The word surreal number will be defined to be what I'm calling a number now. It was a bad career move. When I introduced these things, I just called them numbers. The idea in my foolish little head was that if you put an adjective in front of the word number, it made it refer to less. It's a prime number. Not all numbers are prime, you know. Rational number. Not all numbers are rational. And so I wanted these numbers to be, you know, a very, very large collection of numbers, as they indeed turn out to be. Anyway, so I sort of thought I'll just call them numbers in the context of my book on the thing. It was a very silly thing. And then Donald Knuth invented this lovely adjective, surreal numbers, surreal. And that gets the feeling dead right. They are a kind of extension of the real numbers, and they are also rather bizarre and strange when you haven't met them before. Okay, we have a few more definitions around. I was about to define two. I'm not quite sure if I succeeded. Two definition is equal to 1 plus 1. Oh yes, that's equal to 1 left plus 1. 1 plus 1 left. 1, oh sorry. Yes. Oh, I apologize. It isn't. 1 left plus 1. 1, oh yes it is, plus 1 left, sorry. And 1 right plus 1. Oh, but there aren't any 1 rights. And 1 plus 1 right. Oh, but there aren't any 1 rights. So there's nothing on this side. And 0 plus 1 by theorem 0 is equal to 1. And 1 plus 0 by theorem 0 combined with the commutativity, which I didn't give a name, is also equal to 1. Oh, sorry. There's a comma in between those, not a plus sign. And to say that 1 and 1 are both left options is just to say that 1 is a left option. So 2 is 1 slash blank. After a time, you begin to realize, I began to realize, that what one of these definitions in terms of options means when it's applied to numbers is that the number is being defined to be the simplest thing that is greater than all its left options and less than all its right options. So this says that 2 is the simplest number greater than 1. What time is it? 1:45. So Now I haven't said very much about these, have I? It's hard to say very much about them because every little theorem has to be proved. You can't use previous theorems because you don't know whether they're true or not. They turn out that, you know, the names are very well chosen. Let me just show you roughly what the tree of surreal numbers looks like. There's 0 at the top. Then there's 1 is the simplest number greater than 0. Minus 1 is the simplest number less than 0. 2 is the simplest number greater than 1, so minus 2 will be the simplest number less than minus 1. A half turns out to be the simplest number greater than 0 and less than 1. And there's minus a half as well. Whoops. We carry on like that. In this little finite region of the tree, the numbers I write down in the tree are the mean, the arithmetic mean of the two numbers, that really two numbers that have been defined on. Because if I take, say, 0 and 1, comma 2, then that's the same as 1, comma 2, because if you're greater than 0, you're automatically greater than 1. So you never need more than one left option.
If you're greater than 1, you're automatically greater than 0.
Probably. I made some mistake and my head's not even big enough to remember what mistake I made. So, okay, we're like this. Now, if you proceed along this tree in some way, for instance, suppose we go right from 0 to 1, then left, and then right again, and then left. This is 3/4 is 6/8, so this will be 5/8, and then right, which will be 11/16, and so on. Let me tell you roughly what that means. 3/4 is defined to be, let's say, the simplest number between a half and 1. It turns out it deserves the name 3/4. 5/8 is the simplest number between a half and 3/4. Of course, it's also then the simplest number greater than a half. Oh, never mind. Then the next one will be 11/16 and so on. But you can go down that tree infinitely far. You can have the following thing. It's greater than 0. It's less than 1.
It's invisible.
Okay. It's greater than 0. It's less than 1, I said. Now, the two things I've made define a half just by themselves. But I want it to be greater than a half. So now I consider, the simplest number satisfying these conditions is 3/4. Oh, but I want it to be greater than 3/4, so I'll put 3/4 on the right of it. And the simplest number satisfying all of these is 5/8. And each time, this zigzag path that I'm traveling is saying that each time I work out what the current value is, so to speak, and I want alternately to be less than that and greater than that as we carry on. And then the limit, for those of you who know about limits of the sequence of numbers I'm coming out there, is going to be 2/3. And 2/3 is, well, I just carry on this sequence forever. You understand me? Okay. And 2/3 is the first number we get that isn't a dyadic rational. In other words, a rational with denominator a power of 2. But we get all the real numbers at this stage. Okay, we get some other numbers though. We get, for instance, if we keep on going to the right, we get the number 0, 1, 2, 3, dot, dot, dot. Nothing on the right, okay. That turns out to deserve the name omega. It is, so to speak, the number that Cantor discovered, his first infinite ordinal. you get also omega plus 1 if you put omega on the left as well, and then this will be plus 1, and omega plus 2, and all Cantor's ordinals. What Cantor was doing was always stepping to the right, okay? And when von Neumann redefined Cantor's ordinals, he defined, for instance, 3, the ordinal number 3, to be the set consisting just of 0 and 1 and 2. Well, my 3 is the set for which 0 and 1, is the number for which 0 and 1 and 2 go on the left and nothing goes on the right. So basically, my definitions of Cantor's ordinal numbers are the same as von Neumann's, except that there's a vertical slash put in. You know, von Neumann's just ends before that vertical slash. My definitions of the real numbers, after a sort of rather curious start, which produces the dyadic rationals, are the same as Dedekind's. You know. Okay. So this theory of surreal numbers is really a simultaneous generalization of Cantor's theory of ordinals and Dedekind's theory of real numbers. Okay. You might want to know a little bit more about what kind of animals the surreal numbers are. There's a theorem of Cantor's that says that every ordinal number has, so to speak, a unique expansion in base omega. It's a sum of powers of omega with finite integral coefficients. Well, natural number coefficients, actually. The natural numbers are usually written after the powers of omega, although Cantor initially wrote them before. It's much more sensible to write them after. I have a generalization, that's called the Cantor normal form, or CNF. I have a generalization of it that every surreal number is a sum of, again, powers of omega in a certain sense, except that the exponents, instead of being arbitrary ordinal numbers, are arbitrary surreal numbers. Thus descending, those exponents are decreasing as you pass through the sum, and the length of the sum, which in Cantor's theory is finite, in my theory is an arbitrary ordinal number. You know, that seems as though it's producing a definition of the new numbers in terms of old, but occasionally it does not. With Cantor, he has his epsilon numbers. There's the smallest epsilon number, traditionally called epsilon 0. I don't think it's a very good name, so I tend to avoid it. Let me just call it epsilon for the moment, is its expansion, its Cantor normal form, is omega to the epsilon. So it's not being explained in terms of smaller numbers. I have epsilon numbers too. Let me give you a few examples. Epsilon 0 has the same left options as epsilon 0 does in Cantor's thing, the ordinal numbers. Epsilon 1 can then be defined in terms of epsilon 0. You add new options, which are epsilon 0 plus 1, and omega to that number, and omega to the omega to that number, and so on. I have a number called epsilon 1/2, which has got these options derived from epsilon 0 by omegating it and so on the left, and options derived from epsilon 1 by omegating it on the right. So it's the simplest number between all those functions of epsilon 0 and similar functions of epsilon 1. Oh, yeah, okay. I should say, when you put numbers on the right, rather than adding 1 before omegating, as you did with Cantor's numbers, you subtract 1 before omegating. So omega to the epsilon 1 minus 1 is actually less than etc. Well, never mind. Woo. So there's an epsilon sub x for any surreal number x. And that's about all I have to say, I think. I'll stop there now. Okay.
Thank you very much. As announced, there will be a second talk. We can have maybe one quick question if there's an urgent question right now.
You know, we can always postpone the second talk a bit longer.
Yeah, of course. We already have to some extent.
Yes, that's true.
Any?
Oh, come on, I can't just silence all of you. Are you all asleep? Not quite.
Hugo.
You've expressed some, perhaps frustration is the word, that these haven't been picked up so much in the mathematical community. The theory of surreal numbers hasn't been as applied as perhaps you think they should be. And I was wondering if you have any guesses of...
It's not a suspicion, it's a regret.
Frustration.
Yeah, frustration. Okay.
Do you have any ideas of why? Or do you have any guesses?
Well, people don't know about it is a pretty good reason why, I think. It was quite a popular subject shortly after I wrote the book called ONAG on numbers and games, which introduced the surreal numbers. It was rather strange. It introduced the surreal numbers before the games, because I thought people would be more interested in the surreal numbers. People with a sort of philosophical bent, as I think many of you in this group will have, you know, don't sort of think that games raise any great philosophical problems, and they're not the sort of thing philosophers talk about. Well, except sort of strange philosophers like Ludwig Wittgenstein. Yes, so I think many people haven't been interested. There is, by the way, well, there was one person who got very interested in surreal numbers, and that was Martin Kruskal. He had a plan for solving well, it's usually called the beyond all orders problem in asymptotics. When you take an asymptotic series, like the series for factorial n, well, perhaps I should say a little bit more what I mean by that. Factorial n is approximately, this is Stirling's formula, root 2 pi n times n over e to the nth. Now, you can correct that a bit, and then that gets on to various things. But anyway, it's a modification of Stirling's formula. You open a parenthesis and say times 1 plus 1 over 12n plus some coefficient over n squared plus dot dot dot. And then that apparent power series in 1 over n on the right hand side in that parenthesis never converges. It's called an asymptotic series, but it's still very useful. They're really quite common in applied mathematics. What happens is, you know, if you terminate the series at 1, in other words, after its first term, that gives you a reasonably good approximation for factorial n. However, if instead you terminate it after its second term, you get something that's a better approximation for all large n than the first thing. And in a similar way, if you terminate it after its kth term, it gives you a better approximation than the k minus first term for all large n. But still, if you don't terminate it and take the whole series, it never converges. Question: what does this mean? If you insist on not terminating but having the whole infinite series in there, that's the problem of approximation beyond all orders. People naively think that it must actually have a meaning, and that suppose you take the entire series, multiplied by this previous factor, and say, is it factorial n, or is it one more than factorial n? I think we all agree that it's likely to be factorial n and not one more, especially not 22 over 7 more, and so on. However, according to the hard line definition, as Martin Kruskal called it, it's equally a series for k plus factorial n for all k. They've never succeeded in giving a definition which works, as the phrase is, beyond all orders. Martin Kruskal had an idea. He was a great expert on asymptotics. He had the idea of assigning a meaning to these things in the following way. You, for instance, substitute an infinite integer for n, or an infinite surreal number. You substitute omega in there. And then at omega, Stirling's series converges. Okay? It has a power series at the end, a power series in 1 over omega. It converges. So presumably, factorial omega is the number it gives, if the obvious conjecture is true. But his plan was to prove a theorem that if two functions agreed, two functions of a certain type, good functions he called them, agreed for all sufficiently large surreal numbers, then you wouldn't get any errors by supposing they agreed for all surreal numbers. This was a way of jumping the gaps from finite to infinite. There's a gap. You see, if his conjecture is true, then it's okay to define factorial n to be this infinite series, obtained from Stirling's formula. You just define it now, and then you won't get any contradictions. So that's what the infinite series means. A certain, in that case, it's going to be factorial n. A wonderful thing. However, Kruskal was in Princeton when I was in Cambridge. He communicated with me various ideas then. When I went to Princeton, he would come round every so often and take a whole afternoon, sometimes a whole day, to explain his latest idea on bringing this project to fulfillment. He never brought it to fulfillment. He spent a lot of his lifetime working on this. There's going to be a joint meeting of the AMS and the MAA in Seattle in, I think, January. And there's a special session in that meeting entirely devoted to the surreal numbers. And I gather from the titles of various papers and the abstracts of them that some people claim to have made some progress in Kruskal's problem. I don't know what it is. So maybe at last they will be applied.
I think we should give people who need to leave at 4 the chance to leave now. So as planned, there will be a second surprise talk. It will take place after people have relaxed, and then in a slightly smaller group.
Make yourself slightly smaller.
So take your time, relax, we will ring the bell when we continue with the surprise talk.
The surprise talk is my funniest talk ever.